Hello and welcome to the Minnesota Center for Philosophy of Science's International Postdoc Forum. We are glad you are here. My name is Alan Love. I'm the director of the Minnesota Center for Philosophy of Science. And I just want to say a couple words about our program here, and then I will introduce today's speaker. So it doesn't necessarily seem like yesterday, but maybe it's still fresh in our memories that during the COVID pandemic, there were a tremendous number of cancellations and restrictions on travel that directly impinged on scholarship, and especially for those who were in earlier portions of their career. And at that time, we conceptualized the possibility of this International Postdoc Forum as a way to showcase researchers from around the world working at the postdoctoral stage so that their work would be able to have a broader exposure. And what we found was that after the pandemic, that continued to be a valuable thing. And so we have continued the program, and we're excited to do so. Today's speaker is Edoardo Peruzzi, coming to us from Leibniz University in Hannover. He will be talking to us about formal template accumulation, unification, and scientific progress. So, Edoardo, the floor is yours.
Thank you very much, Alan. Let me just share my screen. Okay, please just let me know if you see the slides.
Yep, it's coming through great.
Okay, perfect. Thank you very much. So welcome everyone, and I'm really grateful to be here with you today, and really grateful for the kind invitation. Especially, I want to thank Professor Love for proposing the idea. And the presentation of today is about a topic that I've been working in the last year and a half as part of my postdoctoral project in Hannover, in the ERC project on model transfer. Let me say that this is a work in progress, so still not in a published form, and every kinds of comments and welcome to make my arguments better are really appreciated. So let me start by giving a bit of background on the questions that I want to ask. Let me start by saying that there seems to be a phenomenon in contemporary science that has attracted the attention of philosophers of science. And different philosophers have specified this scientific phenomenon in different ways, but there is a common ground. The idea is that sometimes in science we observe that the same representation, in this case a scientific model, is able to describe a variety of systems that seems to have not so much in common with one another. This scientific phenomenon has been expressed in different ways. One of the first attempts to specify this problem comes from the work of Paul Humphreys in his book Extending Ourselves, and I will be using later on part of this framework in the context of his analysis of computational science. But similar concerns have been expressed differently, for example, when it comes to the analysis of the role of mathematics in scientific modeling by Christopher Pincock. He speaks about a family of representation being able, by the nature of the mathematical structure they employed, to model, to represent different kinds of phenomena. And then, although in a slightly different fashion, by the work of Robert Butterman, where he analyzes models from physics that are able to describe phenomena that are different at the microscopic level by capturing some meso-level properties, which are invariant across these different phenomena. So the idea is that you have one model for many systems. Here is just a couple of quotes from the philosophers that I've mentioned before. Humphreys in his 2002 article in Philosophy of Science, and then elaborated later on in his book. He says, one of the characteristic features of mathematical models is that the same model in a sense to be explained, can occur and be successfully employed in field quite different subject matters. This feature has significant consequences for the organization of science and suggests a reorganization that is not hypothetical, but is now occurring in some of the more intensively computational areas of modeling. So what he noticed is that certain kinds of mathematical models are able to be employed in many different subject matters for representing different kinds of systems. Similarly, Pincock, taking the case of the harmonic oscillator model, he says it sometimes turns out that there is a family of representations with a constant core of intrinsic mathematics, but where each representation in the family aims at a different kind of physical system. So he takes the harmonic oscillator to be an example of this. It incorporates a mathematical structure that can receive different interpretation, and with this different interpretation, it has been used to describe different kinds of phenomena, going from a spring and a pendulum to electromagnetic fields and nuclear phenomena. So again, the idea is that here you have a representational tool that is given different interpretation, and this interpretation can be used to model different kinds of phenomena. In recent years, this scientific phenomenon has been conceptualized through the label of model transfer. Very roughly, the idea, as I anticipated, is that sometimes in science we observe that the same model or modeling techniques are used in quite different scientific domains. An example, primary example, paradigmatic example of this is the Lotka-Volterra model that has been developed originally in the field of biology and ecology, and then it has been applied in many different areas of science, including, for example, the study of the diffusion of technologies in social settings. So the idea is that there's a source domain, there's a transfer process through which a model gets transferred into a target domain that receives the model. The characterization of model, as we all know, is particularly problematic. For the moment, and I will say something more later on, we take models to be typically mathematical objects that are used in some kind of representative fashion to explain, predict, or intervene into parts of the world that we call target systems. And domains, which is the other element which characterizes the phenomenon of model transfer, are understood and operationalized or proxied in different ways. Sometimes a domain can be a whole scientific discipline, such as economics, biology, physics, and so on. Sometimes we take domain to be sub-disciplines, subfields within the same broad scientific areas. So taking examples from economics, in economics we have subdomains of macroeconomics, finance, industrial economics, and so on. So this phenomenon of model transfer has been studied in relation to many paradigmatic examples. As I mentioned before, the Lotka-Volterra model is an interesting case that has been quite extensively examined. The Ising model is another one, first developed to model ferromagnetic systems and then employed, I would say, in all over the place in science at the moment. For example, now the Ising model is especially used to study the formation and the opinion dynamics within networks. Other examples of model transfer sometimes go to include not individual models, but more like modeling frameworks or constructual manuals for developing models, such as agent-based models that are used in computer science, but also in economics and sociology. Network models, again, used quite extensively in many different scientific fields. And then also game theoretic models, which will be the main examples that I will use throughout the paper. Game theoretic models are used quite extensively in many different areas of science. They were developed initially, let's say, at the border between mathematics and economics, and then they have spread at first in political science and biology, and nowadays they are employed quite extensively also in fields that are pretty far from the original intended domain of application of game theory, such as computer science and engineering. Sometimes, quite interestingly, model transfer can also bring to the development of disciplines in science or domains. For example, the case of econophysics, which is this new domain which sits a bit at the boundary between physics and economics, not finding really a home in neither of the two, which consists in the application of models from physics to study economic phenomena, most importantly, financial markets. And also, we can take evolutionary game theory to be the result of a model transfer from economics and mathematics into biology, and then a reorganization of these tools within the framework of evolutionary theory. So sometimes model transfer can even bring about new domains in science, if you want. Okay. So far we have seen that there is a scientific phenomenon that has been recognized by philosophers of science, and there's in turn a bunch of questions which are open. They have been discussed, but for which, if you want, they still pose philosophical puzzles. The first one concerns the kind of object that gets transferred. The label model transfer may imply that the object of transfer is always a model, but actually, as we already seen with the example that I mentioned, sometimes model transfer is a label that has been attached to quite different cases. Sometimes it seems to be a fully fledged model interpreted, that is the object of transfer. Sometimes it is a modeling framework. Sometimes it is the formal part of the model that gets transferred. So the question is about what is the unit of analysis for studying model transfer to capture what gets transferred. The second questions concerns the transfer process. So what kind of modification needs the model to undergo for having a successful transfer? In some cases, it may be that the model is sick and simplicity transferred to a new domain, and it immediately have a good degree of empirical accuracy. But typically, there's some modification happening in the transfer process, some adaptation of the model to the new domain. And so philosophers of science are currently studying what kind of modification does the model undergo in this transfer. And then the third big question is about the relation between model transfer and general issues such as the topic about scientific progress. Here, the consideration is that if we take model transfer to be an important phenomenon of contemporary science, we may want to understand when is this phenomenon conducive to scientific progress. I will try to say a bit about all these questions, but I won't provide a specific answer for neither of the three probably. Those are big questions, but I will sketch possible answers to the three of them. More specifically, the argument that I would put forward in the next 20-30 minutes is the following. First of all, I will argue that some parts of contemporary science are organized around formal templates. The notion of formal template comes from the work of Paul Humphreys, and I will have to say something about that later on. But for the moment, we can take formal templates to be computational and mathematical structure, which are used for constructing model in a variety of scientific domains. Formal templates are equations, algorithms, network topologies, mathematical games, and so on. These formal bits that are used in model construction. An open question that we have about formal templates starts from the observation that these formal templates don't usually appear as isolated piece of formalism in science, but they typically form organized stocks, organized repertoire that are developed and used by scientists to construct models. So there's a question about how new formal templates that are developed in science gets integrated with existing repertoire. To this end, I will sketch an account of what I call formal template accumulation and show how certain episodes of model transfer can be understood in terms of this accumulation process. Finally, I will detail some implications of my argument for bigger issues in the philosophy of scientific modeling, especially as the title promises about unification through models and progress in model-based sciences. So this is a bit the roadmap, and now I will go into each step in order. So let me start with the notion of formal template. The notion of formal template comes from the work of Paul Humphreys. Paul Humphreys proposed to look at science in a different way, not to look at science as organized so much around the subject matters, domain of phenomena that we want to study, but more as organized around the kind of computational and mathematical structures that we use to construct our models. And his point is that in the end, science is organized around the use of a limited amount of templates, computational and mathematical structures that are used repeatedly in model construction. A few characteristics of these templates are important. First, they typically ensure the tractability of the resulting model. So they ensure, for example, that a certain model has a solution, is solvable. And then they are constructed in a way that makes them sufficiently general and flexible to support the model construction across multiple scientific domains. They are constructed in a way to capture general features that are shared among different systems which belongs to different scientific domains. And again, examples of these templates are network models, certain statistical distribution, agent-based models, differential equations, and mathematical games. So this is a broad overview of Humphreys' account. In his later work in 2019, he specifies the concept of formal templates, characterizing them as lacking an empirical interpretation, or better, having an interpretation which is detachable from the syntactic component. They are highly flexible, and they are typically subject unspecific. With this, Humphreys doesn't undermine the fact that formal templates can be developed having in mind a certain domain of application. But typically, the construction assumptions that enter in a formal template are sufficiently general to guarantee its applicability for various target systems. Given their nature, formal templates are typically developed in formal fields of inquiry, such as mathematics, especially applied mathematics, complexity science, and computer science. But Humphreys noted that sometimes formal templates can also emerge from theoretical templates stripped down of their original interpretation. Here, the idea is simply that sometimes there are theoretical templates which are grounded in a specific theoretical framework, that after being repeatedly used, their empirical interpretation is somewhat stripped down from the template itself, and what remains is the formal component. A nice example of this is exactly game theoretic templates. Game theoretic templates emerge from economics and having economics as its intended domain of application. So they bring about all this baggage of, for example, utility theory and rationality theory. But later on, this theoretical part has been stripped down, and they have been applied in their formal nature in fields where this theoretical framework doesn't make much sense, such as biology, computer science, engineering, and so on. So the idea is that sometimes formal templates are developed specifically just having a mathematical interpretation. Sometimes they are stripped down theoretical templates. The important point for us is just that when constructing, as here Humphreys says, a formal template, we start with general assumptions that are meant to represent abstract features of systems which are shared across multiple systems, that they are not peculiar to specific domains. So they have intrinsic generality that led them to a wide applicability. And as I already mentioned, a nice example of formal templates, which is not proposed by Humphreys itself, but I think it really fits his analysis, is the case of game theory. Game theory can be understood, I would say, as a collection of formal templates. Here we have just a few examples: n-person games, extensive for games, Bayesian games, and evolutionary games. All of them are mathematical structure, which are extremely general, extremely flexible, and they are employed in model construction in very different domains for modeling very different physical and social systems. So we can take game theory as a collection of formal templates. And we can see them even more more precisely by considering a simple example. As I told you, formal templates needs to be distinguished from a fully fledged model. First of all, formal templates don't have an interpretation in terms of any empirical target systems. They have just a mathematical interpretation. We can take, for example, extensive for games, which is a mathematical structure which is composed of the following component. There's a set of players, P1, P2, a set of actions that they can do. Each of them, in this case, has two actions possible, X1, X2 for P1, X3, X4 for P2. And then there's a set of outcomes which results from the action. So this is a formal template, extremely general and extremely abstract. But I can construct a model on the basis of this template when I add an interpretation and a solution concept. So again, a simple example: extensive for games can be turned into a model of an interaction between two firms in the market, where you have a firm which is already in the market, which is the incumbent, and then you have an entrant, which is a firm who has to decide whether to enter the market or to stay out from the market. So I'm interpreting the extensive for game in terms of an economic situation. The entrant has two possible actions, can decide whether to enter or to exit the market. If the entrant enters the market, then it faces the competition with the incumbent, who has again two choices. He can fight the entrant and starts a price war, which is going to be detrimental for both of us, as we can see in the payoff, or it can cave, it can accommodate the entrant. This is a model, and for this model, I can specify a solution concept, for example, the Nash equilibrium, or in this case, a sub-game Nash equilibrium, which specify the outcome of the game, and it led to predictions of empirical situation. It makes the model testable, so to speak. So this is the idea. So what is the value added of taking this framework from Humphreys? Is that we can reduce somewhat model transfer to the process of model construction on the basis of formal templates. We start with a very abstract and general formal templates. In the case of game theory, it's just a game structure plus representation forms, like an extensive for game. When I add construction assumption and an interpretation, I can turn them into various models depending on the interpretation and the construction assumptions that I add. And these models can be used to represent different target systems. Construction assumption is the term that comes again from Humphreys. And briefly, it relates to all these kinds of abstraction and idealization and domain-specific assumption that I have to add to the template to turn into a model. And we can discuss them later on, but for the moment, that is enough. So the idea is that I can reduce model transfer to a process of model construction with formal templates. Now, as I told you at the beginning, if we take this approach, then what emerges, already by considering the case of game theory, is that an interesting feature of science is that these formal templates are not isolated from each other, but they typically form an organized body of knowledge that can be used by applied scientists when constructing models. And this can be seen with many examples. Game theory, as I already anticipated, is kind of an example in this respect. But take, for example, differential equations. The work of Pincock that I mentioned at the beginning specifies that there's a whole field of mathematics, applied mathematics, which, for example, is attempting to describe various kinds of differential equations, what kind of phenomena they can be used to model, and how these differential equations relate to each other. If two of them can be generalized in a more general forms, if two of them are distinct, what kind of mathematical features do they share, and so on. So set of differential equations can also be seen as an organized stock. And then I believe also network theory is such a case. So we may say that at least in some cases, we have this body of formal templates, this stock of formal templates, as I call, that scientists relied upon repeatedly in model construction processes. If this is true, then a bunch of questions arises. Some of them are easier to answer, and some are more complicated. The first question, of course, is what is the process that leads to the development of a formal template? Here, of course, providing a general answer is particularly complicated because we would need to describe somewhat the psychology of scientists and describe an act of creativity where maybe there's not much to say. But I will sketch a bit what might lead this process. But in general, an answer is hard to find. But then there's a second question which I think is more approachable. And is the question of how a new template accrues, integrates with the existing repertoires. So not so much what leads to the development of a new template, but how is the process that integrate the new template with the existing ones? And in this term, I frame the question as a question of accumulation. How do formal templates accumulate in science? How we arrive to have these organized stocks of templates? And the answer that I will sketch, and again, comments are very welcome on this part, is that formal templates often serve as high-level problem-solving tools, and they accumulate through a three-step process that I'm now detailing and illustrating with an example from game theory. So the first step is a step of template design. The situation which typically leads to the development of a formal template is a situation where I have a domain that is facing a new class of problems that wants to address. And suppose that there exists a set of models that is not able to address these problems. In this case, scientists may need a new set of models to address this new class of problems. And this may prompt the design of new formal template. So the idea here is simply that sometimes there has to be an innovation at the level of the formal template to be able for scientists to model a new class of phenomena that is not addressable with the existing modeling set that we have. Once the new formal template is developed, there's typically a phase of integration. The new template has to be conceptually integrated into the existing stock of templates that scientists were already using for modeling phenomena of interest. When this integration step is successfully brought about, there is an updated stock of templates which consists of all the old templates plus the new one. And then after the integration step, the new formal template is ready to be employed in model construction, not just in the domain where it has been developed, but also possibly in new domains. And this is because, as we saw before, formal templates, by definition, they are extremely general and they have wide applicability. So they bend itself to be used for model construction in a variety of domains. So there are these three steps: template design, template integration, and template transfer. Let me illustrate these steps with a case from game theory again, from the history of game theory, which I guess illustrates these three steps quite nicely. Of course, the case study will be a bit sketchy for ease of time, but in the Q&A, we can discuss more the feasibility of this case. Let's start by saying that the very breakthrough in the history of game theory was the publication of the Theory of Games and Economic Behavior by John von Neumann and Oskar Morgenstern in 1944. And we can take this effort from a philosophical perspective as an effort in developing a first collection of formal templates that can be used in model construction, in their view, mainly in economics, but they kept it open to be employed in sociology and political science. They're pretty clear about that. They developed, for example, the mathematical structure which corresponds to n-person games, and also to zero-sum games. So they developed the first game theoretic templates. But then what happens is that the scope of application of these templates in modeling was extremely limited. And this is because all these were games of complete information. So they were games where all the players in the game, they have complete knowledge about the structures of the game. So about the moves of the other player, about the strategies available to the other player, and about the payoff resulting for the other players. And all of this is common knowledge. So when we want to use game theory to model social and economic situation, this assumption, in many cases, it doesn't hold. So there was an emerging class of problems, or if you want to speak in a slightly different jargon, an emerging class of social systems that we want to represent that couldn't be represented with the template that we have at our disposal. This prompt, I argue, the design of novel formal template. In particular, it prompted a bunch of scholars to work on proposing a mathematical structure for games of incomplete information. So games where players don't have perfect knowledge about the structures of the game. And finally, John Harsanyi, who later on got the Nobel Prize for this innovation, about 20 years after Theory of Games and Economic Behavior in 1967, he published a very seminal paper on games of incomplete information, which are also known as Bayesian games. So this is the template design. Games of incomplete information were integrated into the body of knowledge of game theory. Most importantly, they were shown to be a generalization of normal form games, and it was shown that games of incomplete information defined in the way Harsanyi does, they sustain at least one Nash equilibrium. So to ensure the tractability of the resulting models. And after this innovation, there was an uptake shown by historians of game theory in economics and in general in the social sciences in the 70s and 80s. So there's a phase of template transfer after the innovation. Just for reference, a Bayesian game is a generalization of the normal form game. The three main components of normal form games are retain, a set of players, a set of action, and a payoff function that specifies the expected payoff for the players. The two big innovations were that Harsanyi assumes that players have types, and types are parameters that encode all the private information that players have about the game. And then players are assumed to have a probability distribution over the types of the other player and to behave according to Bayesian rationality. And that is the reason why these kind of games of incomplete information are also known as Bayesian games. For example, to go back to our models of firm interaction, on the left, we have a way to model this situation using game with complete information, is the same example that we saw before. On the right, we have Harsanyi's way of modeling the same phenomenon, where we assume that there is a fictitious player, nature, which specifies with certain probability the player to be of certain type, and then the other player has a probability distribution over the type of the other player. And then you have all the different payoffs for the game. Now, it doesn't matter to have the detail, but the point is that the models on the model on the right is more general than the model of the left, is a generalization on the model of the left, and it can be used to address all those situations that we find in real world settings. For example, where we have that the firm, the incumbent, which is already in the market, for example, has knowledge about its own cost structure, but the firm entering the market doesn't have that kind of information. And this is a much more common situation to assume, much more realistic to assume this, than to assume that both the incumbent and the entrant have the same knowledge about their own cost structure. So it radically increases the domain of application of game theory. And then there was a transfer and an application of these Bayesian games, not just in economics, but even beyond economics. First, in very different subdomains of economics, going from auction theory to monetary policy, so the behavior of central banks, and industrial economics. And then on the right, one of the first important application of Bayesian games in political science. But we find application even beyond the social science. For example, they are used a lot in computer science and in security studies. So the idea is that we can reconstruct this case as following the 3 steps that I detailed before. There's a new class of problem emerging in the social science, how to model games with incomplete information. This class includes sub-problems such as how to model entry deterrence, how to model auctions, how to model reputation and signaling in markets. The existing game templates available are insufficient to addressing this new set of problems, and this prompts the design of Bayesian games. Bayesian games are formally connected with the existing body of game templates. In particular, in this case, Bayesian games are shown to be generalization of normal form games, and results on the existence of Nash equilibria for Bayesian games are established. And then there's a phase of template transfer in the 70s and in the 80s, where Bayesian games are employed in model construction across multiple domains, including economics, political science, and computer science. So we have this 3-step accumulation procedure. Now, what is particularly difficult to characterize in a general way, I would say, is the step of template integration. Because template integration can occur in many different ways. And I received some pushback on how I characterize template integration. So here is really, comments are really welcome. Because I come to realize that this step can happen in different ways depending on the case study one is examining. Again, in the case of game theory, in the case that I'm studying here, existing templates are generalized. For example, normal form games are generalized into Bayesian games. And in this way, they cover a broader range of situations. So the integration happens by showing that the new template is a generalized version of the former one. But sometimes new templates can also emerge, for example, by merging, by combining 2 templates, and not really generalizing an existing one. And this is a case that we also find in game theory. For example, later on in the 80s, Bayesian games were embedded with extensive for games. And in this way, you can study dynamic situation where the sequential moves of player matters and where player have incomplete information. And this open up again the domain of application of game theory. So sometimes templates are generalized and sometimes they are merged. And some scholars have suggested to me, but I'm reflecting on these parts, that sometimes templates may just be added to an existing stock without neither generalizing nor merging existing ones. And finally, I've also received comments about templates sometimes just dying and becoming obsolete, in the sense that they are not used anymore because we realize they are not useful for modeling new phenomena. So with this slide, I just want to mention that I'm reflecting on how this template integration work, and I would welcome any comments about that, because my case maybe is more particular, is about generalization, but I'm trying to think in more general. And then here, I don't have space, but in the paper on which this work is based, I developed very quickly some other cases where this accumulation process may exemplify what has happened. But now I just want to close in the first few minutes, first 10 minutes, about the implication of this argument for the philosophy of scientific modeling. First of all, there's an immediate implication about the literature on model transfer. The idea here is very simple, is that some cases of model transfer can be really reconstructed as a process of model construction of the basis of formal templates. And then by focusing on the accumulation process, we can really explain not just how model transfer occurred, but how model transfer is sustainable over time. It's not just that models are constructed on the basis of formal templates, but when new problems emerge, when new class of phenomena emerge that we want to model, this prompts the development of new formal templates that accrue to the existing stocks, and these stocks are then employed for model construction. And so it has a dynamic component that explains not just how model transfer occurred, but how it is sustainable over time, if you want. And this applies nicely to game theory that is applied so widely in science. And when we take this consideration, I would argue, I would sketch, let's say, that there are implications also for thinking about unification and progress in model-based science. Why I take this to be the case? Well, because I would say that formal templates seems to have some form, and I still have to clarify the scope of this, they seems to have some kind of unifying power. This is because the recent literature on scientific models is really focusing on the fact that models are really and often target specific. They are meant to represent domain-specific phenomena. But if we take this approach, inspired by Humphreys, this representation really occurs because these models are constructed on the basis of a limited amount of reusable formal templates. So there's a question about what kind of unifying power these formal templates may bring in model-based science, where overarching theoretical frameworks are often lacking, and so maybe the unifying force may be given by formal templates. And I would say that this may hold for a science such as economics, where game theory, which is, if you want, a construction manual based on formal templates, is really sometimes the only unifying forces across different domains. And there's some literature which goes back to the work of Morrison. Recently, there's this Cambridge element by Taco that speaks about theoretical or formal unity, which occurs when a distinct set of phenomena is found to be representable with the same formal framework. So I'm wondering whether we can speak of template-based unification of some sort. Of course, this kind of unification may be different from other forms of unification, such as explanatory unification, but that is something I'm flirting with. And then we can even say something about progress in model-based science. Why I think this is the case? Well, because I think that in this case we can use we can understand formal templates as contributing to scientific progress if certain success conditions are satisfied. Here, by contributing, I'm using the distinction that exists in the philosophy of scientific progress between constituting and promoting scientific progress. And usually the idea, according to these authors, is that certain methodological or instrumental innovations, they don't really constitute progress per se, but they may contribute, they may promote progress to be occurring in the future. And the typical examples of scientific changes which promotes progress without constituting them are, for example, the development of new scientific instruments, new laboratory techniques, and so on. And I would say that, at least for certain disciplines, formal template and formal template accumulation has as the process to which formal templates accrued in science, may promote scientific progress in a similar way. So formal templates promotes scientific progress in the same way that refining scientific instruments or developing new research methods does. In fields where instruments and laboratory techniques are less available, such as economics, formal templates can constitute the counterpart, if you want, of this methodological innovation. Of course, and again, this is preliminary, but I would say that not all cases of accumulation contribute to progress. Something must be in place. So I'm in search for, if you want, success condition that can really tell when these episodes of formal template accumulation really are conducive, are contributing to progress. And just to sketch two conditions that seems to me to be important. The first is that what I call modeling expansion. So the novel formal template needs to be able to be used for modeling a broader range of situations that were previously inaccessible. And this is the case that happened when Bayesian games were developed. A new set of phenomena that were previously not representable, now they come to be represented. So there is an expansion in the modeling scope of game theory. And then a second condition is that the new template must be able also to reformulate existing models using the new template. And this is what I call formal unification. And this is to be equally important because it's what gives the unifying power to the formal template. And here again, Bayesian games is a nice example, because once Bayesian games were integrated into the vocabulary of economists, then economists started to reformulate with this new language existing models that were part of their modeling framework with just one formal template. So many models of auction, of insurance market, or reputation that were using different mathematical frameworks were then reformulated using the same template. And this, in some sense, unifies these different contributions. So those are two possible success conditions that I would say need to be in place for formal template accumulation to contribute to progress. And with that, I'm just going to conclude, wrapping up what I've done in this talk. First, I try to show that we can understand model transfer as a model construction process on the basis of formal templates. I provide a tentative account of how such formal templates accumulate in science so that we can explain how model transfer occurred and how it's sustainable over time. And then I explore briefly some implication for the philosophy of scientific model. Much work remains to be done, besides specifying better the different components of my framework. I'm currently working on the empirical counterpart of this. We are producing a map based on bibliometric analysis on how game theoretic models have spread across scientific domains. And then there's a goal of analyzing the various modification strategies, as I mentioned before, the second big question in the literature. What kind of modification strategies model undergo during the transfer? And then another elephant in the room is that this account of model transfer is completely independent and doesn't rely at all on analogical reasoning, whereas another stream of literature really emphasizes the analogical component of model transfer. So there's an emerging attempt of reconciling these two different strands of literature, and this is also part of the future work I want to do. Thank you very much for your attention, and I really welcome to your feedback. Thank you very much.
All right. Thank you very much, Edoardo, for that presentation. And so now we will transition to the next portion, which is a short commentary from the Minnesota Center for Philosophy of Science postdoc, Yasmin Ozel. Yasmin?
Yeah, thank you. Yes, thank you very much, Edoardo, for the talk. I'm, in fact, going to also end on the note that you ended on, namely on the question of what role analogies play in this context. So let me share my slides, first of all. Okay, so the central thesis of the paper was that model transfer consists in a process of formal template accumulation, and that is exactly what I will be focusing on. So I will be focusing on the question what the formal template part will do, and I will be asking a question about accumulation. So, Peruzzi argues for a new perspective on model transfer. So instead of seeing the model as the unit of transfer, he focuses on what he calls the formal template. And he then argues that when we see model transfer across scientific disciplines, what is actually taking place is this phenomenon that he calls a formal template accumulation. So the examples we saw were, for instance, game theoretic structures. So where Peruzzi showed that, or like tried to show on the example that the current analysis is focusing on the wrong units of analysis and that we ought to focus on the formal templates. And the payoff of focusing on formal template accumulation was an explanatory one. So the idea was that if we focus on formal template accumulation in the transfer of models, this will allow us to also explain mechanisms underlying the transfer of theories. Of models, of scientific models. Okay, so just to have a few quotes in front of us before I ask my questions. So formal templates, in contrast to model templates, are purely mathematical structures. So that point will be important for my question in a second. So the mathematical structures that are both computational tractable and sufficiently flexible to support model construction across a range of target systems. So the payoff of introducing the formal templates here is that we can, of course, use it across all sorts of scientific domains because it will be maximally general in its applicability. So the purely formal objects, says Peruzzi, with only a mathematical interpretation. So there is no other information contained in them. So by contrast, the model templates that the debate that Peruzzi criticizes focuses on. So these model templates, they are understood as mathematical structures coupled with a general conceptual idea that is capable of taking on various kinds of interpretations. So the examples Peruzzi cites are the Ising model, Volterra equation, and so on. So my question now is essentially focused on the notion of, so my first question is what notion of accumulation is at work here? So my concern is there might be a tension between Peruzzi's notion of accumulation and model transfer and his understanding of formal templates as mathematical objects. So I have a quotation here, but in the talk he described it even better. I will go to that in a second. So he says, so how are new formal templates developed? How do they integrate with, now Zoom is in the way, how do they integrate with the stock of existing templates? In other words, how do formal templates accumulate in science? Yeah, so in the talk, Edoardo told us that so what is happening is, so we have integration or an accrual. So this is how he spelled out accumulation here. The concern that I have here is, so Edoardo describes a very striking phenomenon. Namely, there appears to be a set of favored mathematics that scientists draw on. So they don't draw on just any mathematics, but there seem to be certain equations that they favor. So what is that motivation, and why is it the case that some mathematical concepts spread and others don't? My suggestion here would be what Edoardo, what you ended on, namely, maybe we are making judgments of analogy here. So I would be interested to hear what your argument against analogies is here. And so now the question is, if the formal templates are just pure mathematics, but the argument is that when they're being transmitted, they accumulate. What really does accumulation mean here? Because I don't think the argument is that the math itself changes. See, I have another quotation here. So, right. So they accumulate. The repertoire of game theoretic templates expands over time. So and transferring models involves more than simply reapplying a formal template. So my question here is, how is this possible if we are not dealing with model templates, which of course will be slightly different in each case, but we're really only talking about the mathematical equation. How should that accumulate? Because presumably the mathematical equation is not going to change. Okay, so my second question is related, namely, so Edoardo is arguing for an expansion of our model ontology. So in arguing that we focused on the wrong unit, he essentially identifies this intermediate level called the formal template that, as I understood it in the paper, is supposed to be more than the mere mathematical expression, although how exactly maybe you can explain, but it's also not a full theory. And so the question is, what's the payoff of expanding our ontology in this way? Well, on the one hand, the advantage is that we can now capture all of these different cases in which the same equation is being used. So I understand that as the motivation here without having the baggage of the content of the concrete theory. But on the other hand, we do want models to represent. So in order for that to be the case, maybe it isn't possible to get rid of all of the content. And that's exactly why model templates do involve descriptions and equations, as they're often so in the literature on models described as both being necessary in order to have a model. So I would be interested to hear more about that. And lastly, in this context, my concern, the examples we see in the paper, so the game theoretic analyses, but also the other discussed cases. Well, game theory is, of course, not mathematics. It's an application of mathematics, and so are all the other cases. So why should we understand these game theoretic analyses as mere mathematics? How exactly is this claim meant? Yeah. Okay. Yeah, that's it.
Okay, thank you, Yasmin. So I'm going to give Edoardo a moment to respond to Yasmin's basic questions a little bit, but I wanted to highlight to others in attendance, if you have a question, please feel free to use the raise hand function. Alternatively, you can also use the question function that is in Zoom, or you can put something in the chat. I will be happy to read out those questions for you. Whichever format is preferred is fine. And you can begin to put your hand up or put those questions in even while Edoardo is briefly responding to Yasmin. So, Edoardo, I'll give things back over to you.
Thank you very much, and thank you very much, Yasmin, for the very nice points. I will try just to reply, but some of the points really needs to be addressed in more detail and are open. But I will just try to make a couple of points. So the most important point, it seems to me, you were asking is why to use the notion of formal templates in the first place. I think there are a few advantages and a few cases where it's more appropriate than the competing notion of model template. In particular, I think that the notion adopting the formal template as the unit of analysis really helps you see the process of model construction. So you start with this bare backbone of a mathematical structure, which is a game, and then you add bits of stuff to construct a model. And it is in this construction process that you turn your template into models of different systems. The notion of model template, especially in the last few years, has inflated a lot. And now the distinction between the model template and the model becomes very blurry. And at that point, I think it's not particularly useful to understand model transfer. We could just go to the notion of model itself. Whereas the intuition, at least how I read Humphreys at first, he proposed templates as this middle ground, if you want, notion between theories and particular models which are about something. So templates are not interpreted in terms of an empirical target systems. And that's why I think for games, these work nice because, and here maybe it responds slightly to the third point, I would think that game theory is mathematics. Of course, game theory is I would say is a mathematical theory that receives a lot of application. Its origin is at the boundary between economics and mathematics, but I think we can take game structures, solution concepts as being part of a mathematical theory. Of course, it's a branch of, if you want, applied mathematics, so it has intended domain of application, but I guess we can separate the particular applications and the game theoretic structures. And about accumulation, there is a very good point. So, and probably a big open question that I have, because I wanted. So I think in the paper, especially, the accumulation concept that I use is really monotonic. It's just addition to existing stocks. But then when presented in a couple of times, I gave some feedback on the paper, people started to point out that context where the accumulation seems to be different, and maybe accumulation is not even the best term, because sometimes templates are combined together. Sometimes one template is generalizing to another one that covers the previous one. Sometimes the template just die because they are not used anymore. So there seems to be different ways in which stocks emerge, and not just the accumulation process that I detailed. So here is really a problem that I have. It might be driven by the notion of formal template that I use. So this is an open question that you pointed out, that because maybe by taking this notion of template as a formal mathematical objects, then I have some puzzle in explaining what is the connecting tissues that keeps these formal templates together. So that is really something that I've been thinking about. And finally, about analogy, I don't have specific arguments against analogy. I think it's important in many episodes of model transfer. It can explain nicely why scientists, after all, do transfer model from other fields. It's just that much of the existing literature has worked with this template-based account that, in Humphrey's idea, was meant to not necessarily to get rid of analogies, but to put analogies in a less important spot. Because for Humphreys, what really matters when you transfer a model which is based on a template is really to check whether the construction assumption makes sense in the new domain, to justify again the assumptions that enter in your model. And in this way, you may think that scientists do the transfer reasoning analogically, but in the philosophical reconstruction of the transfer, we don't really need analogy. But I've been thinking more and more that probably we should keep them back, so I don't have a specific argument against them. But thanks again for very nice points. I hope I replied to some of them, but for many, I don't have an answer. So thank you again.
All right, so let's open up the conversation more broadly. So in the queue, I have Nanjun Wei. So I will see here. You should be able to talk now, Nanjun, to us if you turn on your sound.
Oh, hi.
Hi.
Yeah, go ahead.
Hi, Edoardo. Thanks for the very nice talk. So I think my question is also related to Jasmine's comment. So I was wondering, and you also mentioned the particularly tricky part in your sequence is the second part of template integration. So my question is, what do you think? Why do you think you need this second part? Because if your whole argument is that formal template is for model transfer, then it seems that the first and third part will suffice, right? So the first part is about template construction in order to cater for in order to account for new phenomena to be applied for new situations. And the third part is how you actually apply that to the domain of phenomena that you want to do, right? So, and you also mentioned that there could be the various different ways of integration. If you need integration, then integration could either merge or just simply addition, or sometimes it goes to extinct. Then this may seem like just a labeling thing, right? So so if the target is only about transfer of knowledge, transfer of model from one domain to the next, then the integration part doesn't seem to be very important. You mentioned a little bit maybe in the end about unification is useful, but then you also said that in this way you think about formal templates as not as constitute, as not but not really promoting scientific progress. But in this way of formulating the state of events, you are still thinking about progress mainly in terms of the domain of application, right? So I think there can be an argument for the epistemic upshot in the integration. As you in your reply to Jasmine, the game theory itself should be looked at as a domain of inquiry, which has its own interesting, generates its own interesting problems, so on and such, and also related to other domains of application. But right, so I think maybe the emphasis on that could be part of the answer to why you need integration.
Mm-hmm. Yeah, thank you very much. That's a very good point. So my intuition for why an integration step is important, now necessary, maybe it's strong, but although this part of my account, is that I started from thinking, okay, maybe we can understand some cases of model transfer really in terms of formal templates. And then I start to look at cases, and then since I'm mostly concerned with philosophy of game theory and economics, I was looking from to these cases. And then if you look at game theory from some kind of abstract level, it's really this set of templates. And so I guess one point for me is that transfer episodes somewhat, I guess that the integration is in many cases important also to justify a successive transfer. For example, in the case of Bayesian games, the point about showing that they are generalization of normal form, so they are related to what economists already knew and using, and that the models sustain the same Nash equilibrium solution concept as other classes of games, was an important component that explains and justify why then economists started using them. Not just that they were able to represent new phenomena, but that this new template was part of the body of templates that they already get acquainted with. It may be relevant for if I want to make points about unification, but you're probably right that certain parts of the argument about transfer don't really depend. It probably is not a necessary aspect. Maybe sociological important, or
maybe this also links to Jasmine's comment. So in the sense that the integration is, when the integration happens, it's not just a formal template anymore. You can think of it as a theoretical template, and a lot of the extra like epistemic upshots from thinking about it as theoretical template, as you say, that the knowledge that we are already familiar in the game theory domain can be applied. So this is partially contributing to the successful of transfer.
Yeah. Okay, thank you, Najim. I appreciate it. I think we should see if we've got other questions. Okay. Other questions that people have, either raise hand or put it in the chat. If not an immediate one, I will ask a question that I have, Edoardo. So one thing that seems important about your account is that you have a clear set of criteria for individuating formal templates, so that you know when to count them, and so that if you sort of say this is a sort of new formal template as opposed to this is a formal template where it has been tinkered with, but maybe we don't want to call it a new formal template, but simply a variation on the theme. So I wonder if you could say a little bit about how you think about individuation for formal templates.
Okay, yeah, that's a good point. Yeah, that's a deep point. I don't have an answer. You're right in the sense, because I assume already in the template design, I assume the existence of a new formal template, and what could say, well, maybe the case of Bayesian games, that would be no concern about being a new template because it incorporates these new elements that are not part of the mathematical structure of the previous one. But in other cases, I think you're right in saying that maybe the boundary between being a new formal template and being a variation of an existing one can be really tricky. For example, again, from game theory, consider a two-person game and an n-person game. I think then at that point, the only thing that changes is the number of players that we assume are in the game.
Yeah.
And I would say that in that case, for example, it's tricky to think of, okay, is the second one, they were developed at the same time by phenomena, but imagine that the second one was developed afterwards, historically. So you could think, okay, it's a new template or is a variation of an existing one. So that is tricky. And maybe also, again, depending on the kind of template notion, because if I adopt this notion of formal templates, then there has to be something at the level of the mathematical structure, the formal structure that differs. But individuating then, I think that's a good point. I I haven't addressed, to be honest, but it's probably very crucial.
Yeah, and maybe too, it can be potentially helpful
Mm.
because it might be that the ability to change a formal template in a sort of larger number of ways might point to why certain formal templates are more transferable than others. So it could end up being also part of
Mhm.
what explains transferability for that small subset or that favored subset of models. So yeah. Okay, Yasmin's got her
Thank
hand
you
up.
very much.
Yasmin, go ahead.
Yeah, I
Yeah.
just wanted to just a tiny follow up. It was very helpful in your response that you stressed the inflation of the use of model template as a notion. So I think I mean the intuition to say that there are just a very limited number of mathematical equations that are featured in science. That's an important intuition, and now I forgot my video too. Sorry. So and I think like one way you could make that strong is to just spell out this inflation a little bit more and just justify that we should have a category that captures this. Sorry, that was just a follow up on Alan.
Yeah, yeah. The structure of the, I really struggled with finding the right structure of the paper, and then maybe also part of some issues that I may have in convincing the reader, so to speak, because it's a paper that sits in between different literature, because it's this point about model transfer, but there is also this point about the use of the same mathematics for different systems, and I had some struggle. So maybe I have to focus more on one dimension or another, and then spell out more specifically why we need formal templates. Now I have just in the last section, as you saw, maybe it has to arrive earlier on to justify also why we need a new concept, let's say. Yeah, thank you very much. That is helpful.
Okay, any other questions that people would like to ask Eduardo? Okay, well, if not, then I will bring our time to a close. And let me say thank you, Eduardo, for your
Thank you very much.
presentation. And thank you to Yasmin for her comments. I think we had a great exchange of ideas. And I look forward to our next installment of the International Postdoc Forum coming in April. Details are on our website. We hope to see you back then. Take care, everybody. Bye-bye.